Welcome back to the show, everyone. Today, we're diving deep into the exciting world of autonomous driving. This technology is rapidly evolving, and one of the key challenges is how to effectively learn features from the complex 3D data that these systems rely on. Traditional approaches have often struggled with sparse point clouds, and that's where the research we'll be discussing today comes in.
Exactly, John. The ability to learn from vast amounts of unlabeled data is crucial for autonomous driving, and that's where self supervised learning comes in. But working with 3D data presents unique challenges. The inherent sparsity of point clouds and the variability in point distribution due to sensor placement and occlusions by other scene elements make it tricky for existing methods to extract meaningful information.
That's a great overview, Emily. And that brings us to our topic for today, UniPAD, a universal pre-training paradigm for autonomous driving. This paper by Hongwei Yang and his colleagues proposes a novel self-supervised learning framework specifically designed to overcome the limitations of traditional methods when dealing with 3D data. Hongwei, welcome to the show. Can you tell us about UniPAD and its core goals? Thanks, John, for having me. The main goal of UniPAD is to provide a universal pre-training paradigm that can be applied to various modalities, like 3D LiDAR point clouds and multi-view images. We wanted to create a framework that could learn effective representations from this data and transfer that knowledge to different downstream tasks, like 3D object detection and semantic segmentation. So, UniPAD is essentially a way to train a model to understand the 3D world without requiring massive amounts of labeled data. It's like teaching a model to recognize objects and scenes simply by looking at the world around it, similar to how humans learn. That's a good analogy, John. UniPAD is built on a very clever approach. It utilizes a three-part architecture. First, we have a modality-specific encoder, which takes either a point cloud or multi-view images as input and extracts features from the visible regions. This encoder is designed to handle the unique characteristics of each data modality. So for point clouds, you'd use a 3D backbone like VXLNet, and for images, you'd use a 2D convolutional network. And you mentioned a mask generator. What's the role of that? The mask generator is a key component for making the training more challenging and encouraging the model to learn more robust representations. We strategically mask out parts of the input data, forcing the model to infer the missing information. It's like covering a portion of an image and asking the model to fill in the gaps based on the visible parts. This makes the learning process more difficult, but ultimately results in a more robust model that can handle real-world scenarios where data might be occluded or incomplete. That's fascinating. It's like a controlled form of data augmentation, challenging the model to learn beyond the limitations of the visible data. And how does the framework then handle the difference between 2D and 3D information? I mean, you can't just throw a point cloud into a 2D network, right? You're right, John. That's where the second part of the framework comes in, the unified 3D volumetric representation. Instead of trying to force different modalities into the same format, we convert both 2D images and 3D point clouds into a common 3D voxel representation. This allows us to preserve as much of the original information from each modality as possible. For the multi-view images, we use a technique called lift-split-shoot, which effectively unprojects the 2D features into 3D space, creating a dense representation of the scene. And for point clouds, we simply retain the height dimension from the point encoder. So essentially, you're creating a 3D grid, a sort of volumetric map of the scene. That's very clever. But then, how do you actually learn from this 3D representation? How does the model understand the geometry and appearance of the scene? That's where the third part of the framework, the neural rendering decoder, comes into play. This is where we utilize the power of neural rendering, which has seen tremendous advancements in recent years. Essentially, we sample rays through the 3D voxel representation, and for each ray, we predict the color and depth values based on the features extracted from the voxels. It's like simulating the process of rendering a 2D image from a 3D scene. And by minimizing the discrepancy between the rendered projections and the ground truth data, we encourage the model to learn a continuous representation of the scene's geometry and appearance. So essentially, you're using the model's ability to recreate the scene as a proxy for learning its underlying structure. That's a very interesting approach. And you mentioned that you implemented memory-efficient ray sampling strategies. Can you elaborate on that? Sure. Neural rendering can be computationally expensive, especially when you're working with high-resolution images. So we devised three strategies to optimize the process. We have dilation sampling, which samples rays at intervals, reducing the number of rays that need to be rendered. Then there's random sampling, which simply selects a subset of rays randomly. But we found that the most effective strategy is depth-aware sampling, which prioritizes sampling rays from areas of the scene that have more relevant information, like objects closer to the car, rather than distant background elements like the sky. This allows us to focus the learning process on the most important parts of the scene. Honghui, you're making this sound very straightforward, but I'm sure the actual implementation was quite complex. Can you give us a sense of the technical challenges you faced and how you overcame them? You're right, John. There were definitely some challenges. One of the biggest ones was finding the right balance between the complexity of the model and the computational resources required for training. We had to carefully choose the size of the voxel grid, the number of rays to sample, and the depth of the neural network. We also had to consider factors like data augmentation and the loss function used during training. It was a lot of trial and error, but we were able to achieve a good balance of performance and efficiency. That's impressive. So Honghui, let's talk about the results. What did you find when you tested UniPAD on real-world datasets? Did it achieve the desired performance improvements? Absolutely. We conducted extensive experiments on the NuScenes dataset, which is widely considered to be one of the most challenging datasets for autonomous driving. We tested UniPAD on both 3D object detection and semantic segmentation tasks, and the results were very promising. We found that UniPAD consistently improved the performance of baseline models, achieving significant improvements in NDS and MIOU scores. We even achieved state-of-the-art results for segmentation on the NuScenes dataset. Wow, that's really impressive. So UniPAD seems to be a very effective approach for pre-training models for autonomous driving. But how does it compare to other methods that have been proposed in the literature? That's a good question, John. We compared UniPAD to several other self-supervised pre-training methods, both image-based and point-based. We found that UniPAD outperformed all of them in terms of performance on both 3D object detection and semantic segmentation. And importantly, UniPAD is more flexible than most other methods, allowing us to apply it to both 2D and 3D modalities. This versatility is a key advantage, as it allows us to leverage the strengths of both types of data. It seems like you've done a thorough job of exploring the different aspects of UniPAD's design and its performance. Honghui, I'd love to hear your thoughts on the ablation studies. What insights did you gain from examining the influence of different design choices on the framework's performance? Certainly, John. We conducted several ablation studies to better understand the contributions of each component of the UniPAD framework. For example, we investigated the impact of the masking ratio, and we found that a lower ratio, compared to previous MAE-based methods, worked best for our framework. We also experimented with different depths and widths for the decoders, and we found that deeper decoders were better at incorporating geometry and appearance cues during pre-training. And finally, we explored the effectiveness of different ray sampling strategies, finding that depth-aware sampling yielded the best performance by focusing on the most relevant parts of the scene. That's very insightful, Honghui. The ablation studies really reinforce the importance of careful design choices in achieving optimal performance. Emily, as an expert in this field, what's your take on the significance of UniPAD and its potential impact on the future of autonomous driving?
John, this is really exciting work. UniPAD's ability to effectively pre-train models for autonomous driving using both 2D and 3D data is a major advancement. It's clear that Hongwei and his team have thoroughly addressed the challenges of working with sparse and complex 3D data. This framework has the potential to significantly accelerate the development of autonomous driving systems, enabling them to learn from vast amounts of unlabeled data and adapt to real-world scenarios more effectively. This could be a game changer for the field.
That's a very optimistic outlook, Emily. But I'm sure, like any groundbreaking research, UniPAD also has its limitations. Honghui, are there any aspects of the framework that you see as potential areas for future improvement? You're right, John. UniPAD isn't perfect. One of the limitations is that we need to explicitly transform point and image features into volumetric representations. This can increase memory usage as the resolution of the voxel grid increases. We're also exploring ways to further enhance the efficiency of the ray sampling process. And ultimately, we want to investigate the applicability of UniPAD to other domains beyond autonomous driving. We believe that this framework has the potential to be broadly applicable for learning effective representations from complex data in many different fields. That's a great point, Hongwei. It's important to remember that while this research is a major step forward, there's always room for improvement. Emily, do you have any thoughts on potential research directions that could build upon UniPAD's success?
Absolutely, John. One promising avenue is to explore the integration of semantic supervision into UniPAD. Leveraging the outputs of state-of-the-art 2D semantic segmentation models like SAM could provide valuable additional information to the 3D voxel representation. Another area of exploration is to investigate alternative representations for the 3D scene, potentially using point-based methods that might be more efficient for handling large-scale datasets. And of course, it's exciting to consider the broader applications of UniPAD in fields like robotics, medical imaging, and even virtual reality. The possibilities are endless.
This is truly fascinating stuff, folks. UniPAD represents a significant step forward in the quest for reliable and robust autonomous driving systems. Honghui, you and your team have made a remarkable contribution to this field. Thank you so much for joining us today and sharing your insights. And Emily, thank you for providing your valuable perspective and highlighting the potential impact of this research. It's been a pleasure, John. We're excited to continue this research and explore the many possibilities that UniPAD presents. And thank you to our listeners for joining us. We hope you found this discussion insightful. Be sure to check out the paper and stay tuned for more exciting developments in the world of autonomous driving.